Let's explore power sets and understand why a set with n elements has 2 to the power of n elements in its power set. Let's start with our given set G, which contains the elements 1, 2, and 3. We write this as G equals the set containing 1, 2, and 3. The power set of G, written as P of G, is the set of all possible subsets of G, including the empty set, and G itself. Let's construct this step by step. Let's organize our subsets by size. First, we have subsets of size 0. This is just the empty set. Then we have subsets of size 1, which are 1, 2, and 3. Next, subsets of size 2, which are 1, 2, 1, 3, and 2, 3. Finally, we have the subset of size 3, which is the entire set 1, 2, 3. Now, let's count the total number of elements in P of G. We have 1 subset of size 0, 3 subsets of size 1, 3 subsets of size 2, and 1 subset of size 3. Adding these up, 1 plus 3 plus 3 plus 1 is equal to 8 total elements in P of G. Now, let's understand why this equals 2 to the n, where n is the number of elements in our original set. For each element in G, we have 2 choices, either included in our subset or not, since we have 3 elements, and for each element we have 2 choices by the multiplication principle. We have 2 times 2 times 2 equals 8 possible combinations. This is the same as 2 to the third power, or 2 to the n, where n equals 3. This pattern holds true for any set with n elements. For a set with n elements, each element has 2 choices, and we multiply 2 by itself n times, giving us 2 to the n elements in the power set. Therefore, we've shown that for our set G with 3 elements, its power set P of G has 8 elements, which equals 2 to the third power, supporting the general rule that a set with n elements has 2 to the n elements in its power set.